All right, so we just looked at some properties of infinite limits. So let's practice some of those infinite limits here. Determine each limit. All right, so we got a collection of 3 of these. I'm not sure that's enough space to write. Let's come over here where I can generate more space. So the first one, limit as x approaches 0 of 1 plus 1 over x squared. Let's give it a try. X approaches 0, 1 plus 1 over x squared. Again, first thing that I want to do is to think of a direct substitution here. So, of course, there's nothing to do with it. 1 plus 1 over a 0 squared. So the limit of the first piece, of course, that's just 1, but 1 over 0, some number over 0, I want to understand, of course, that that shoots off to infinity, either a plus or a minus infinity, right? Let's see. This should be either a positive or a negative infinity. Which one is it? Well, notice that the number that's on the bottom here is always being squared. So no matter what we put in here, this is always supposed to be some sort of positive number, of course, except at 0. So from either side of 0, that should be approaching some sort of positive number, which implies that this thing is a 1 plus infinity. Now again, we're not really adding or treating this as a number. It's this limit that's allowing us to say that, hey, this thing is approaching infinity, and I add 1 more to that thing that's approaching infinity, it's still infinitely big. So the answer on this one is infinity. It is, it's increasing without bound. Remember, that means that that limit does not exist due to unbounded behavior. And basically, that was the sum or difference property of infinite limits there. Okay, let's look at the second one. Limit as x approaches 1 of x squared plus 1 over cotangent pi x. I'm going to tackle this in 2 different ways, like directly, and then I might show you the, if you don't like cotangent, of course, we can switch to sine and cosine. All right, so the first way we will look at it, limit as x approaches 1 from the left, x squared plus 1 over doop doop cotangent of pi x. So a direct substitution, let's just see what the heck is happening here. I would have 1 squared plus 1. It doesn't matter if that's from the left or the right. You still just, when you're thinking about this, seeing what's happening, you're still thinking of a direct substitution of the number 1. So I'd have a 2 up top, and then on the bottom, it is the cotangent of pi times x, which cotangent is pi. So let's see. Cotangent, I want to think of as a cosine pi over a sine pi. Boop. All right, so maybe I look at a unit circle here, and at pi, that's over here on the left-hand side. It has the coordinates negative 1, 0. Cosine is the negative 1. Right? Negative 1. And then the sine pi is a 0. I have a number that's not 0 divided by 0. I know that that's going to a positive or negative infinity. So we can do like a little sign analysis here. That's why they chose the left-hand side, to see if this is going to a positive or a negative infinity. You're going to see in a minute that in this particular case, it really doesn't matter. But we'll go ahead and do it for the practice. So remember, on the left side of pi, that essentially means the top part of this unit circle. It's in quadrant 2, that's right here. So in quadrant 2, our cosine is negative, but our sine is a positive number. So we would have essentially a negative divided by a positive, so that should go towards a negative, meaning that this is a negative infinity. So now let me explain why that really didn't matter, because we're taking 2 over negative infinity. Didn't matter if it was negative or positive. Remember, our quotient property right here says that that's going to approach 0. So back up here on this one, it is equal to a 0. All right, so let me show you how we could have done it by avoiding cotangent altogether right here. So I could have rewritten this as a sine and a cosine stuff on the bottom. Limit as x approaches 1 from the left, x squared plus 1. And instead of cotangent, write cosine pi x over sine pi x. And it's a complex fraction, so we want to multiply to get rid of that. So we're going to multiply by our fancy one of a sine pi x over a sine pi x. Okay, and on the bottom they'll cancel, which leaves our sine pi x up on the top. Now, with enough practice with those complex fractions, you could have probably just gone, oh yeah, that one that's on the bottom, it's just going to shoot up to the top, and I'm done. Okay, so I have the product x squared plus 1 sine of pi x over cosine pi x, and then just do a direct substitution here. It doesn't matter that it's 1 from the left, you still directly substitute in a 1. So in the parentheses, I'd have 1 squared plus 1, so I'd have 2, and the cosine, sine of pi over the cosine of pi. Okay, so we had already discussed that the sine of pi is 0 and the cosine is negative 1. So I have 2 times 0 over negative 1, still pretty much a 0. All right, third one, it's a natural log. The limit as x approaches 0 from the right of the natural log of 0. So a direct substitution would give us the natural log of 0, which is a no-no because that is not in the domain. Remember, the domain for natural log is x has got to be greater than 0. Hey, we can look at a graph and, well, actually, I just happen to have a graph right here. It's over here above this flipping math logo. It's right here. This is the natural log graph. And you can see that nothing for that graph exists on the left side over here in quadrant 3. And the reason why is because it's the inverse of the exponential function. And the exponential function has a horizontal asymptote at y equals 0, the x-axis. So when I flip it across the line y equals x, then that means that the natural log has a vertical asymptote right here at x equals 0. Okay, well, we can see pretty clearly that as x approaches 0 from the right-hand side on the natural log graph, this is going to shoot down towards negative infinity. Okay, so that finishes up example 2. So I do want to note that we have yet to tackle limits at infinity. Right? And the reason why is because, look, here we're taking this limit as x approaches 1 from the left, limit as x approaches 0, limit as x approaches 0 from the right. So this whole first part was just getting us used to working with infinities, and now in this next set of videos we'll actually look at as limits as x approaches either a positive or a negative infinity.